All right, good morning, or good evening, or whenever you're watching this. We're going to start talking now about chemical equations, chemical reactions, that sort of thing. Again, I think this is all going to be a review for you guys. I don't think you're going to have a lot of trouble with this. Antoine Lavoisier, I believe that's how you say that. He was kind of right and kind of wrong when he made this statement. He said that nothing is created, an equal amount of matter exists both before and after the experiment. Now, that's usually true. Law of conservation of mass holds true in most situations. The time that it doesn't, we know, is in a nuclear reaction, which we're going to talk about that in the next unit, where some matter can get converted into energy. But the law of conservation of mass is fairly useful for most of the things that we're doing. Okay, so chemical equations basically just show what's happening in a chemical reaction. And so you have this, up, CH4 plus O2 giving CO2 plus H2O. This is a combustion reaction, by the way, which we're going to get to in just a minute. But combustion, combustion is when you have some sort of organic molecule combining with oxygen and makes carbon dioxide and water, okay? And this is basically just, this is the normal way that we're used to seeing these things written. This is a more, down here, this is a more pictorial example of showing the molecules and how they're combining and that sort of thing. And then down at the bottom, I guess, is sort of a way of keeping track of balancing the equation. So I'm going to show you a little bit different method for doing that, which you guys, anyone who had me last year, you'll know. Reactants appear on the left side of the equation, okay? And then products appear on the right side of the equation. I think we're all pretty good on that. I think we talked about this a lot last year, so you guys should be very familiar. Okay. And then the states of the reactants or products, you're going to write those in parentheses to the right of each compound. So CH4, you put a G in parentheses here because CH4 is a gas in this particular reaction. O2 is a gas, CO2 is a gas, H2O is a gas. Okay. So obviously this reaction is going to generate some heat. It's going to take place in a fairly hot environment because they're all gases. Okay, and then coefficients are inserted to balance the equation. Now when we talk about coefficients, we're talking about the numbers in front of the formulas, okay? Now it's very important that we understand the difference between coefficients and subscripts. All right, these numbers right here are the subscripts, okay? This 2 right here, the 2 over here on CO2, and the 2 on H2O. Those are subscripts. We never, ever, ever, ever change those, okay? Ever. All right, let's go on a little bit here. Subscripts and coefficients give different information. So this is why we don't change the subscripts, okay? If you have a chemical symbol H2O, that means one molecule of water, okay? So there's sort of an understood 1 right here. And that's what the coefficient tells you, okay? Now the subscript basically tells you the composition. It tells you that there are 2 H's and 1 oxygen in every H2O molecule, okay? And the coefficients tell us the number of molecules. So if there's a 2 in front of the H2O, that means there's 2 molecules of water here, okay? And so total, you'd have 4 H atoms and 2 O atoms. I think we're good on that. I think I stressed that quite a bit last year, so hopefully that's making sense, okay? And again, just to reiterate, actually, I don't think it's on here. Your blank here says, when balancing an equation, only change coefficients, okay? Only change coefficients, never change subscripts, okay? Sorry, I thought that was on the PowerPoint. So that's what that blank is. Alright, so now we're going to do a sample problem here where we practice balancing an equation. And I'm just going to do it on this slide because that's easier. So we've got Na here. I'm not going to worry about the states of matter too much yet. plus H2O gives us NaOH plus H2. Okay? Now the way I showed students who were in my class how to do this last year is I basically showed you if you write down the elements underneath the arrow in the middle and just make sort of a tally for yourself. So we've got Na, H, and O. Those are our three elements that we have here. Okay? And then you just count up how many of each one that you have. And so we've got one sodium on this side, one sodium on the right side. Okay? We've got two hydrogens on the left, three hydrogens on the right. We've got one oxygen on the left, and we've got one oxygen on the right. Okay? So that's how that works. Now we just have to figure out how to balance this thing. Okay, give me just 1 second here. Okay, sorry about that. Got interrupted there. Okay, let's go ahead and get back to balancing this reaction here. So what we had here, sorry, I'm going to have to rewrite this. So we've got Na plus H2O gives us NaOH plus H2. Okay, and then we just make a tally of the elements down underneath the arrow. Sodium, hydrogen, and oxygen are our three. Okay, we've got one sodium on the left, one sodium on the right. Two hydrogens on the left, three hydrogens on the right, one oxygen on the left, one oxygen on the right. Okay, the only thing that's unbalanced right now is the hydrogens, and we've got kind of an odd even situation here. And I think what I taught those of you who were in my class last year, if you get the odd side to an even number, that's usually the easiest way to take care of these things. So if I put a 2 here in front of this NaOH, that's the simplest way to make this number an even number. So now I've got 4 hydrogens on this side. Because remember, the coefficient changes everything that you put the coefficient in front of, okay? So now we've got 2 hydrogens from the NaOH and then 2 hydrogens from the H2. That's a total of 4. Now we changed a couple other things here. Now we have 2 sodiums, and we also have 2 oxygens, okay? So you just sort of keep track with your tally there. So now I'm going to have to balance that. To balance the sodiums, it's pretty easy. I just put a 2 in front of the Na, okay, and that gives me 2 of those. And then to balance the H2Os, if I put the hydrogens and the oxygens, if I put a 2 in front of the H2O, that gives me 4 of the hydrogens, and it gives me 2 of the oxygens on the left side. And now everything you notice here, the numbers match. 2 sodiums on each side, 4 hydrogens on each side, and 2 oxygens on each side, okay? So then you've got 2, 2, 2, and kind of an understood 1 right there. You don't have to write the 1 in, but that's the idea of how to do the balancing, okay? The next question here, it says the following diagrams represent a chemical reaction in which the smaller spheres are oxygens and the larger spheres are nitrogens. Write the chemical formulas for the reactants and products. Well, I'm realizing here that it is very difficult, based on this printout, to tell which ones are larger and which ones are smaller. So we might just go ahead and skip this one for now. Maybe we'll come back when I actually have a picture that you can read. I've never seen anything exactly like that on the AP exam, so I think you guys will be okay there. Alright, so let's go ahead and talk about reaction types. The different types of reactions. You can't see this. Combination reaction is the first type that I want to talk about. And we're only talking about 3 types today. We're going to cover single replacement and double replacement on a different day. Okay? So combination, you've got 2 or more substances reacting to form one product. Okay? Now an example of that, actually there are several examples on the next page, but I want you to write this one down also, this example. Oh no, never mind. It's already on there. Okay, so the examples here, you already have them written on the next page. The N2 plus 3H2 forming NH3. C3H6 plus Br2 forming C3H6Br2. That one's a little unusual. I wouldn't expect you to be able to predict that one. And then we've got the one that's pictured here, and you guys saw this last year, and maybe I'll show this to you again this year. You got magnesium, and you're adding oxygen to it. okay, in the presence of heat. And when you do that, it forms magnesium oxide, okay? And that's, if you guys remember this from last year, that's when we burn magnesium in the presence of oxygen. It burns very, very, very bright, okay? So that's that reaction. That's the idea of a combination reaction. It's very simple, really. You're just two things coming together to form something else. Okay, next. I think. Why this is not working? Okay, that's just another picture of the magnesium reaction happening. Alright, next is decomposition, okay? And I think you guys probably remember this from last year as well. Decomposition, you've got one thing to begin with, and it breaks down into two or more things, okay? So an example of that, on here, you've got sodium nitride, NaN3, that's breaking down into sodium and nitrogen gas, okay? And that reaction happens inside of an airbag. Okay, and so that's what the picture is showing here. It's not a very good picture, but that's basically how an airbag works, or one type of airbag. Now this sodium is going to need to react with something almost immediately as well, because you don't want to have just solid sodium. It'll react with oxygen in the air to become something a little less harmful. But that's the idea there, okay? That's a decomposition. Okay, so now let's try some sample problems here. Balanced equations for the following reactions. And what I might need to do here, actually, is go ahead and open up. Sorry, bear with me for a second here. Probably want to open up a Smart Notebook file, just so that we can do some of these examples off the PowerPoint. So the first one on here says write a balanced equation for the following reaction. The combination reaction that occurs when a lithium, metal, and fluorine gas react. Okay, now the nice thing about this one is they're actually telling us this is a combination reaction. Okay, you won't always get that information, but on this particular one they are telling you that. Okay, they're telling you that this is a combination. So the way that we would write this, we've got lithium metal, okay? That's just going to be written as lithium. And because it's telling us it's a metal, we can put the state of matter solid there. It's not always going to be obvious what the state of matter is, but if you can figure it out based on the information they give you, go ahead and put it. So lithium metal plus fluorine gas. Okay, now, here's the tricky thing about writing these equations. You're going to want to write F and then a gas symbol there. But what you got to remember, fluorine is one of the diatomic molecules, which means that naturally it does not occur by itself. So we're going to have F2 here. Okay, it's diatomic. So lithium plus the F2, and we got to figure out what that combination reaction is going to be. Okay, this is not that difficult if you remember your ionic compounds. Okay, what you're going to have here is you're going to have lithium combining with fluorine. Lithium forms a 1+ charge if you look at your periodic table, because it's in the first group. Fluorine forms a 1- charge because it's in the halogen group, group 7. Okay, so lithium is essentially going to transfer one of its electrons to the fluorine. Okay, so what we're going to end up with here is a 1-to-1 combination, lithium fluoride. Okay, you don't necessarily have to worry about the state of matter that happens there. So lithium fluoride is our product. Now the only other thing that we have to do here is write a balanced equation, okay? And so this is obviously not balanced the way it is. We've got 2 fluorines on the left side and 1 fluorine on the right. Now I don't know that we need to make our tally for this one, because this one seems pretty simple. If I put a 2 in front of the LIF here, that gives me 2 fluorines, but that also gives me 2 lithiums, so then I have to put a 2 here, okay? And so that's letter A. Now, if we're going to write a balanced equation for the next one, this is a decomposition reaction, and again, they're nice enough to tell you that this is a decomposition. Solid barium carbonate. Okay, now, there's a couple of tricky things about this. Decomposition, I think, is one of the hardest ones to actually predict, and we're going to talk more tomorrow about how you actually predict these, okay? But if we've got a decomposition reaction occurring here, barium carbonate, we got to think about a couple of things here. I'm just going to think first, I'm going to kind of write this off to the side, what charge barium forms when it forms an ion, and barium is going to be a 2+ ion, okay? And then carbonate, This is one of these polyatomic ions you're going to need to know. CO3, 2 minus, okay? So when we crisscross those and reduce it, it's a 2 plus and a 2 minus, so this can be a 1-to-1 ratio. So BaCO3. Okay, and it says it's solid barium carbonate, so go ahead and put your S there. Now this is a decomposition, so we're only going to have one reactant to start with, and it's going to break down into a couple of different products. Okay. Now the hint here is it's going to form a solid and a gas, and this you might not remember. Again, we're going to go over these rules a little bit more tomorrow. I'm just showing you this as an example now. Barium carbonate, you might think that that would split into barium and carbonate, okay? But what it actually does here, any carbonate, and we learned this rule again last year in my class. I'm not sure if Ernst talked about it or not, or Allensworth. I think they probably did. But the idea here is when you have a metal carbonate, it's going to break apart to form a metal oxide, which in this case is barium oxide, okay? Now, I got to figure out what the ratio is here. Barium's a 2 plus, oxygen's a 2 minus. So that's going to be a 1-to-1 ratio, okay? So barium oxide, usually going to be a solid, plus a gas, okay? Now the gas that would be left here is carbon dioxide, CO2. And the nice thing about this is it's already balanced. If you look at this, there's one barium on the left, one barium on the right. One carbon on the left, one carbon on the right. 3 oxygens on the left, 3 oxygens on the right. So we don't have to worry about balancing this one, okay? All right, so that's the idea of decomposition. Now again, that's difficult. So we're going to have to talk more about that, and we will tomorrow. I have a reading for you that will help you guys out on that, I think. Okay, so now let's go back to this. Let's talk a little bit about the last type of reaction that you can have here. If I can get it to work. Okay, this is just showing an example. Probably should have showed you this first because this is another example of a metal carbonate breaking down into a metal oxide, CaO, and carbon dioxide gas. Okay. Another example here, KClO3 breaking down into KCl plus O2. Okay, now we're going to have to talk about that rule tomorrow. And then you've got NaN3, and that's the one that's shown in the picture here. That's the airbag thing. Okay, so there's some examples of decomp reactions, decomposition reactions. It'd be cool, you call them decomp reactions. Okay, combustion. So this is the last type that we're going to talk about today. We've got 2 other types to cover, single replacement and double replacement. But combustion are rapid reactions that produce some sort of a flame. Okay, those are our favorite types. A lot of times they involve hydrocarbons reacting with oxygen. And hydrocarbons, again, we talked about this the other day. Hydro sounds like hydrogen. Carbon sounds like carbon, okay? So compounds containing hydrogen and carbon, okay? And when they react with oxygen in the air, that's the most common type of combustion reaction you're going to have. Most things that burn are organic. They have carbon and hydrogen in them, okay? Not always, but most things that burn. Okay, some examples here, and I think I have these written on your sheet. CH4 is methane gas. Obviously, that's going to burn in the presence of oxygen. And then C3H8. C3H8, I believe, is propane. And that also, we know, burns in the presence of oxygen. Took me a minute to remember there. I'll teach you a mnemonic when we get to the organic molecules to know what the names of each of these alkanes are. We talked a little bit about alkanes the other day. Oh, let's talk about a sample problem here. Okay, so let's get out of this for a second here. No, go away. Need to align this thing evidently. Okay, so back to this. We've got an example problem here. Write the balanced chemical equation for the reaction that occurs when methanol, CH3OH, is burned in air. Alright, so methanol, CH3OH, and that's a liquid, okay? Now combustion reactions always, if they're complete combustion, which is the only type we're going to talk about right now, they're always going to have a certain way of reacting, okay? And it's very easy once you learn it. But basically you're going to have some organic molecule typically. This one's organic because it has carbon and hydrogen in it. Also has an oxygen, but as long as it has carbon and hydrogen, it's usually going to be organic, okay? So this is an organic molecule. It's going to react in the presence of oxygen, and it's going to form two products, carbon dioxide and water. Again, that's for complete combustion. That's not exactly what happens in real life, but it's close, okay? So we got CH3OH plus O2 yields CO2 plus H2O, and we just want to balance this thing. Now these combustion reactions are a little bit tricky to balance sometimes, okay? So what we want to do here is go ahead and write our elements. Carbon, hydrogen, and oxygen are our only three, okay? I would always balance the carbon first, and the hydrogen and oxygen don't matter as much. So let's go ahead and count these up. One carbon on the left, one carbon on the right, 4 hydrogens on the left, 2 hydrogens on the right, 3 oxygens on the left, and 3 oxygens on the right, if I'm counting correctly. Okay, so we need to balance this thing, and these are always a little bit trickier to balance when we've got oxygens in there, in the organic compound, I mean. So we got to be real careful here. So the first thing that needs to be balanced, obviously, is the hydrogen, okay? We're going to put a 2 in front of here. That's going to give us 4 hydrogens, but that messed up our oxygens. Now we have 4 oxygens on the right side, okay? And now, unfortunately, we've got kind of an odd, even situation going on here. And so we're going to have to probably put a 2 in front of this CH3OH, which is going to screw everything up, okay? So now we've got 2 carbons over here. We've got 3, 4, 8 hydrogens on this side. 8 hydrogens, and now we've got 2, 4 oxygens. Okay, that fixed our oxygens, but it messed everything else up. So now we're going to have to rebalance here. Okay, let's balance the carbons. We've got to put a 2 over here to balance the carbons, but now that messes up our oxygens again. Now we've got 4 oxygens from the CO2 and 2 more from the H2O, so that gives us a total of 6. Okay, let's go ahead and balance the hydrogen now and see if that fixes things. To balance the hydrogen, oh boy, sorry about that. Well, that's interesting. Can we put this down? Click on this. You know what? I'm just going to, rather than risking messing this up, I'm just going to scribble this out, okay? You can erase it on your paper, but we're going to put a 4 here. That's going to give us 8 hydrogens, okay? And now that gives us 8 oxygens, okay? So we're almost there now. Now the thing that we can do is we can go ahead and deal with this O2 right here on the left side, and that will give us the number of oxygens that we need since we've got an even number on both sides. So I've got 2 oxygens from the CH3OH. I need 6 more, so I'm going to put a 3 right here in front of the O2. That gives me 6 oxygens from the O2, 2 oxygens from the CH3OH. That gives me a total of 8, and now everything's balanced, okay? Again, those combustion reactions can be tricky sometimes, but that's the way that they work. All right, that is it for today. Like I said, we're going to spend quite a bit more time covering those things tomorrow in a notebook, or in a, I guess I'm going to copy it for you, but I've got this book of chemical equations, and it does a really good job of teaching you how to predict what's going to form. So we're going to talk in more detail about those 3 types of reactions that I just covered today. All right, that's it. See you next time.